All right, I'll go ahead and get started. So good morning, everybody. Today, we are going to be continuing our exploration of heat transfer, looking at both steady state and transient conductive heat transfer. We have a couple more things to touch base off in terms of the steady state conduction, namely looking at conduction around cylinders and through cylinders. And then hopefully we'll see how far we can get into the discussions for transient conduction. So from last time, we've been talking about heat transfer by conduction. Where we state that in a given system, the conductive heat transfer can be governed by the thermal conductivity, the surface area, in terms of the temperature gradient over the thickness where conduction is occurring. Now, when we consider conduction through cylinders, we have to discuss how, for a given cylinder, let's say we have conduction from the inside to the outside. It's a little different, primarily because the surface area at any point is changing as you move from either the inside to the outside of a cylinder or the outside to the inside of a cylinder, such that we can describe conduction or flux through a cylinder similarly to how we do for a regular rectangular object using rectangular coordinates. However, when we solve the differential in the radial direction, what we find is that the Q conduction for a cylinder results in application of a natural log, such that when we correct for the surface area, we find that heat transfer via conduction of a cylinder can be approximated as negative 2 pi L times K times the gradient delta T divided by the natural log of the outer radius over the inner radius. And this adjustment is namely due to the fact that the surface area is going to be predominantly dependent on the variation in surface area in the radial direction. So let's take a look at a quick example using this adjusted form of our heat conduction equation. So if I have a steel tube with a 60 millimeter outer diameter and it's to be insulated with a 50 millimeter layer of foam, which has a thermal conductivity of 0.055 watts per meter Kelvin, followed by 40 millimeter layer of cord, which has a thermal conductivity of 0.05. The question then asks if the temperature on the outer surface is 150 degrees and the temperature of the inner surface of the cork is 30 degrees, what is the heat loss through the insulating layers? So, give you guys a second to jot some of this stuff down.
So the insulation is inside the steel tube?
I'll draw it for you. Admittedly, this isn't written in the best way. I should probably update it. Yeah, I'm going to adjust this problem to make it a little easier. So I'm going to draw this to kind of show you what I'm getting at. And I'll update it in Blackboard. So what it's supposed to look like is, let's say we have a pipe, and this is going to be steel. And then we have a layer on the outside of this, which is foam. And then around that, we have a layer of cork. So the outer radius of the steel is about 60 millimeters. The thickness of the foam is 50 millimeters. Actually, the radius would be 30 because the diameter is 50 or 60, excuse me. And then the foam layer is 50 millimeters in thickness, which means if I was going to identify the radius for that foam, it would be 50 on top of 30 or 80. And for the cork, it would essentially be the 40 on top of the 80 or 120 millimeters. And so the temperatures, as identified in my fixed problem, is the pipe surface is at the pipe foam interface is 150 degrees, and on the outer surface of the cork is only 30 degrees. So we can identify Q as 2 pi KL times delta T over the natural log of RO over RI. We can also, even for the cylinder systems, consider this as a system in series where we can identify the thermal resistance of a cylinder as essentially the natural log of R over Ri divided by 2 pi K times L. Now, I didn't give a length of this pipe, so we can take a basis and look, say we're looking at 1 standard length or 1 meter of pipe. And so basically in this, we would be solving for heat transfer per unit length, just to make the calculations a little simpler. So with that in mind, I can look at, well, if I know the temperatures on the outer surface of the pipe, the outer surface of the cork, therefore, delta T is simply 120 degrees. And all I have to consider is the thermal resistance of the foam and the thermal resistance of the cork. So for the foam, I have ln of R over Ri, or 80 over 30, divided by 2 times pi, times L, which is 1, times the K, which for foam was given as 0.055 watts per meter Kelvin. Which if I run this, I get approximately 2.83 kelvins per watt. So if I look at the thermal resistance of the cork now, I would be looking at R over Ri again, but instead now I'm looking at 120 millimeters over 80 millimeters divided by 2 times pi times 1 meter, now times 0.05, which is the thermal conductivity of the cork. And I get 1.29 kelvins per watt, which tells me my R total is approximately 2.83 plus 1.29 or 4.12. With that in mind, I can simply solve for the heat transfer via conduction as 120 degrees Celsius divided by 4.12 kelvins per watt. Or approximately 29.1 watts, and then taking in my basis per meter of pipe. Any questions on that example? I admit it wasn't written in the best fashion, so I tweaked it and I drew it. That's why it's important to draw some of these out. Right. All right. Now the last section in this conduction lecture discusses what's known as finned surfaces. Now fins are really important because they're an effective way of allowing essentially heat dissipation through the development of a lot of surface area. I'm not going to talk a whole lot about finned surfaces, primarily because time constraints, but I will definitely say they are extremely important. Now, fins are typically made of, materials that have high degrees of conductivity. And what you're looking at is a comparison between the conduction through the base of your material along the fin length, as well as what we expect in terms of convection off of the fin. And so essentially the purpose of a fin is to allow improved heat transfer and heat dissipation through the addition of surface area where conduction can occur. And so when you're looking at an analysis of a fin, you're looking at a comparison of the conduction into the system minus the essential heat dissipation or convection that occurs out of the fin. And so to write a differential balance on the fin, it can be written essentially as ddx, which is the length along the fin, times your k times a dt dx minus HP T minus T infinity equals 0. And what's important to kind of note once again is this is the conduction into the fin, hence why it's positive, and this is the convection out of the fin, hence why it is negative. And so there exists a lot of different ways to analyze a fin, whether you're looking at something adiabatic or looking at simple corrections to a system. We're not going to get into it primarily because it's a little lengthy in the discussion, but it's important to consider both the fin efficiency and the fin length of a system, where you can consider the efficiency of a fin eta as the heat conduction that can exist and that exists in the fin over the maximum heat transfer that exists within the fin. And once again, this is at steady state. And at steady state, the conduction into the fin and the convection out of the fin will equal 0. And so what we find is that for a fin system, the efficiency can exist in one of two forms. However, they share one thing in common, essentially the inverse of this m value by the length, where m is simply just a summary term of the key characteristics of the fin, which is the square root of HP over K times AC. Where
Just to clarify, is P there the density, or
P is the perimeter of the fin,
okay?
and AC is the cross-sectional area.
Is that just, never mind.
H is the heat transfer coefficient, and K is the thermal conductivity. There's also another value that looks at in terms of fin effectiveness, which is essentially an analysis of heat transfer that exists with and without fins on a surface. It's really not helpful, primarily because in general we know that having fins on a surface is always going to be improvements in heat transfer in terms of no fins. What's better to consider is the efficiency of the fins.
Is that hyperbolic tangent or tangent times h?
It's hyperbolic tangent. That's a good question. Yeah, there's a lot of hyperbolic functions that exist when analyzing fin systems. We're not going to do a whole lot on them. You know, that's why I'm briefly touching base on them. They're useful. They're important. If you want, there's an example that I put in the lecture notes that you can work out and we can talk about. But it's for the most part, they're kind of plug and chug systems. We don't do a whole lot of analysis around fin surfaces. They're just an efficient means of adding surface area to a system to improve heat transfer. So I think that's all I'm going to say on them. And with that in mind, I'm going to shift gears now. And now we're going to talk about transient heat conduction. where we consider systems that are not at steady state. And there's a few ways in which we can analyze systems. The first case is going to be through use of what is known as a lumped system analysis. And so lumped system analysis is simply a way to consider transient or unsteady state conduction. By identifying convection as the limiting factor in heat transfer. And that might sound a little silly because we're looking at transient conduction and we're saying, well, the convection is the issue. So the best way we can discuss this is, let's say we have a sphere and the sphere is hot, right? And we can consider from the center of the sphere to the outer region of the sphere, essentially, I'll make it green, that there can exist a temperature profile in the sphere, right? Such that if I was going to graph the temperature of the sphere versus, let's say, the radial direction, we can identify and consider, well, if this sphere is hot and we're putting it in an area where initially the sphere temperature is much greater than the ambient temperature, we can consider, well, if at T equals 0, it's going to be some, temperature, and we're going to say for in the sphere, it's all going to be the same temperature. However, at T greater than 0, we're going to say, well, at a certain point, that the surface, right, is going to transfer heat out into the surroundings, such that we start to see changes in that temperature profile, right? So T equals 1 minute, T equals 10 minutes. I'll clean this up to make it a little more legible, right? And so over time, as that sphere cools, we can expect some form of a temperature profile to exist in that sphere. However, the nature of the temperature profile largely depends on two things: on how quickly convection occurs on the surface relative, I hate that, to conduction within the sphere. Meaning, if I have my expected convection rate is going to be much greater than my expected conduction rate, the outer surface will be much cooler as compared to the center. And so I can expect a very pronounced temperature profile. However, if my conduction rate is much greater than my convection rate, I can approximate the object or the sphere as having a uniform temperature throughout. And so, in this case here, the profiles will be like I've drawn here. For the second case, we might find that, the temperature over time might look a little more like this. Where, the temperature's falling uniformly throughout the object. And so in that case, I can consider the system or the object having a uniform temperature, or as we call it, we consider it a lumped system. And how we can relate the conduction as compared to the convection is through use of what is known as the Biot number, where the Biot number is a rate comparison of the convective heat transfer at the surface of an object over the conduction within the object, which we can calculate as H times LC over K, where L sub C is the characteristic length. For pipes, tubes, those kinds of things, it's going to be the diameter. For spheres, it's going to be the diameter. For other systems, we're actually looking at, it's going to be the volume over the surface area. So when we can consider using this Biot number is we can identify when the lump system analysis can apply. And in general, a lumped system analysis applies when our Biot number is less than or equal to 0.1, meaning when convection becomes our limiting factor in our heat transfer system. And so for a given system, we can identify the temperature and temperature profile as the following expression: T of our system minus T infinity, or the ambient or surrounding temperature, divided by the initial temperature minus the ambient or surrounding temperature, equals E to the negative heat transfer coefficient times surface area divided by our density divided by our heat capacity divided by our volume times temperature. Or if it makes it easier, you can just write it E to the negative B T, lowercase b, where B is equal to HAS over rho C sub P times V. So for a quick recap, one of the simplifications we can make to transient conductive heat transfer is for systems where convection is the limiting factor associated with heat transfer, we can calculate the Biot number to determine whether we can use what's known as lump system analysis, which allows us to essentially approximate the temperature profile within a given object as a single value. And in that case, what we're simply solving for is how the average or mean temperature of the object changes with time as a function of the heat transfer coefficient, as well as the properties of the object itself.
Dr. Lopez,
Yes.
just to clarify, the little t is time?
Yes.
Okay, thank you.
Yep. Yes, T is time, H is our heat transfer coefficient, A sub S is surface area. The rho, which is supposed to be on the denominator, is density, heat capacity, and volume. We can even say it's times the characteristic length we want. So let's take a look at an example of using our lumped system analysis. All right, so we've got a person who's found dead at 5 p.m. in a room with the room temperature maintained at 20 degrees. If the temperature of the body is measured to be 25 degrees C when found, and the heat transfer coefficient between the body and the room is 8 watts per meter squared Kelvin, what's the approximate time of death, assuming the body can be modeled as a cylinder with a 30 centimeter diameter and a length of 1.7 meters? All right. So, example. Dead guy. So, we got a guy. Unfortunately, he's gone. Found an electrical at 5 p.m. Diameter we can approximate as a 30 centimeter, 3.3 meter cylinder with a length of 1.7 meters. The T sub T, or the temperature found, was 25 degrees. The ambient temperature was approximately 20 degrees C, and our initial temperature, which, assuming temperature around 98 degrees Celsius.
37.
That's a good value. I think that, yeah, 37 degrees C. You figure I'd know what room temperature, what body temperature is in Celsius, but alas, the American way. So the question is, estimate the time of death. Now, one of the first things we can do is solve for the characteristic length to volume over surface area, which for a sphere, we're looking at pi d squared over 4 times L divided by the surface area, which is essentially the area of both ends of the cylinder and then the area of the length, or 2 pi d squared over 4 plus pi dl. So for this system, I have pi times 0.3 meters squared over 4 times the length, 1.7 meters, divided by 2 times pi times 0.3 meters squared divided by 4 plus pi times 0.3 meters times 1.7 meters. So we do this, we'll end up with meters cubed on the top, meters squared on the bottom. So we get our value in meters. we should get a value of approximately 0.069 meters. So with this in mind, we can identify the Biot number as H times LC over K, or 8 watts per meter squared Kelvin times 0.069 meters divided by the K, which, did I give you the thermal conductivity? I did not. So we're going to assume K is approximately 0.617 watts per meter Kelvin. So if we do that, we find that the Biot number is approximately 0.9. So in this case, technically, the lump system analysis does not apply. We would have to consider the temperature profile in the system, but for the purposes of practicing using LCA, we're just gonna calculate and estimate the time anyways. So our LCA equation is T minus T infinity over T naught minus T infinity equals e to the negative B times T, where B is equal to H over rho Cp L sub C. And I'm going to approximate this person as water. He's mostly water. And so I'm going to say B is equal to H, or 8 watts per meter Kelvin, divided by the density, was 1,000 kilograms per meter cubed, divided by the heat capacity of water, which is approximately 4,184 joules per kilogram Kelvin, divided by the volume, or excuse me, the characteristic length, 0.069 meters.
Dr. Lopez, your notes window closed out.
Yeah, it's a little overheated, getting a little toasty in here. I apologize. Do you see it now?
Yeah, we can see it now.
All right. So I can solve for this B value and I get approximately 2.77 times 10 to the minus fifth. And you should end up with inverse seconds. And so with that in mind, I can solve what I'm looking for is T. Rearranging this LCA equation, what you find out is you end up with negative BT equals the natural log of T minus T infinity divided by T naught minus T infinity. And so what you're left with is T is equal to the negative natural log, just to distribute the negative over, of T, which was found at 25 degrees C, minus 20, divided by 37 minus 20, divided by 2.77 times 10 to the minus fifth, inverse seconds. And this will give you your answer in seconds, which I can get approximately 44,110 seconds, or 12.3 hours. Which tells me if the body was found at 5 p.m., time of death is approximately 4:42 AM. So that's how we can use lump system analysis to estimate time of death on this poor man, as well as for other systems. Any questions on LCA? All right, if not, let me at least introduce the next method of approximation that we can use, which is known as one-dimensional transient conduction. And for this, let's say I have a system, like a cylinder or a slab or something, and it's initially at some temperature, but it's being heated such that I have heat coming into my system on both sides. If I assume one-dimensional heat transfer exists, what I find out is that at any given time, the temperature profile in this system will exist following laws of symmetry, such that at some initial rate, let's say it's uniform, so this would be my T equals 0. Over time, I'll have some temperature profiles emerge. However, they'll follow laws of symmetry. And what that allows us to do is to consider, well, if our object is symmetrical, all I have to really find out is essentially the temperature profile in half of my object, because the temperature profile on the other half will be the same, just flipped around. And so we can use symmetry to develop a simplified expression for the heat transfer that we anticipate in our system. And what we land up with is an expression that says, well, assuming symmetry an expression that looks like this. And this should be a T. And so what we have is terms associated with heat transfer coming into the system on the surface as a function of time, as well as the heat transfer that's occurring within the system. So we have convection once again onto the surface, conduction within the surface. However, we can't consider this a lump system. And this results in our analysis. And so we have, let's see, we can simplify it by saying the remaining heat transfer, the resulting heat transfer is going to be a function of the material itself, i.e. density heat capacity considerations. And so what we find is an approximation that states the partial derivative of the temperature with respect to time can be approximated by a value which is a function of the second partial derivative of position. But we find that this term, K over rho Cp, is a combination of intrinsic values. Meaning that since the heat transfer that we see in a transient system is a function of a combination of intrinsic values, we can define that as a new property of heat transfer, alpha, where alpha is known as our thermal diffusivity. And thermal diffusivity is a function or defined as the ability of a substance to diffuse thermal energy within itself. And, as we've shown in the equation above, that's equal to thermal conductivity over rho times Cp. It's very similar to thermal conductivity, but it also has to take into consideration not necessarily heat transfer through it, an object, assuming steady state, but in non-steady systems. Now we're looking at not only the ability of that system to conduct heat, but also hold and diffuse it within itself. And so with this in mind, what we find is in solving these differential equations for a one-dimensional system, it can be done, but the solution for the differential equations associated with one-dimensional heat transfer results in what's known as a series solution. Meaning we can solve the system, but we get an infinite series. And so what we do is we identify for particular geometries the important terms that exist within that series solution. And it looks very similar to what we ended up with in a lump system analysis, but in this case, we're looking at systems where, for example, if I'm going to look at a slab or one-dimensional slab, I end up with Ts minus T over Ta, where Ts is the surface temperature, Ta is the initial temperature, and T is the local temperature at X at time T. And that's what makes this, complicated, because we're not only considering the temperature as a function of position, we're also considering it as a function of time. hence the emergence of the second derivatives that exists within the system. And we find that for this system, the solution results in a value known as 4 pi over e to the negative a1 times FO times the sine of pi times x over 2s plus 1/3 e to the negative 9 a sub 1 times FO times the sine of 3 pi x over 2s plus 1/5 times e to the negative 25 a1 FO times 5 pi x. Pi x over 2s. And those are the first three terms you typically need, only these three. In some cases, you can even get away with the first couple. So a sub 1 is simply just pi over 2 squared. S is 1/2 of the thickness of the slab. And FO is a particular dimensionless value known as the Fourier number, which is simply alpha, or the thermal diffusivity, times time divided by s squared. I think I'll probably leave it there. We'll pick up and rediscuss this one-dimensional heat transfer on Wednesday.
Hold on, can you give me a minute to copy that down
Oh, of
before
course,
you?
as much as you'd like. I'm not going to move. No worries. This is a lot. This is also on page 310 in your textbook. There's quite a bit of series solutions, but fortunately, there's a lot of more straightforward figures that you can use in lieu of the series solutions. Which is also an example of why solving differential equations for these kinds of systems is really complex, particularly because this is only a one-dimensional system. Having to do a three-dimensional analysis would be a nightmare. Any questions in the discussion that we've had today? All right, if not, that's all I have for you guys today. I'll jump over into office hours in about 5-10 minutes. But if not, take care, have a great day, and I will see you all on Wednesday.
Thank you.
Thank you.
Thank you.
All right, bye guys.